All right, so last time we were talking about using change of coordinates formulas as a function, and more specifically as a change of variables function, to use with our brand new tool called change of variables that allow us to turn one integral into a different integral. Okay, so we talked through a lot of these details last time. We computed all of the Jacobian determinants. Well, I referred to computing those Jacobian determinants, left that as exercises for y'all to do. It's a good, healthy exercise in algebra. Everyone should give that all a try. And then I also made the observation that if you make certain highly advisable choices, then you can ignore the absolute values. I emphasize these are choices. You don't have to. If you want to leave those absolute values in there to make your life difficult, you can, I suppose. Can't imagine why anyone would want to. So please always choose only non-negative values of r for those coordinate systems, and choose your phis between 0 and pi. And then those absolute values just go away. Okay, so I think that's about where we were, if I remember correctly. And so moving along, here's our first example. We're going to entertain this first quadrant portion of the unit disk. So this region right here. And you don't have to do a change of variables here. You could do a typical rectangular slice and dice, and that leaves you with this integral, which at a quick glance doesn't look all that bad until you realize, again, these inner bounds are going to be part of my outer integrands. And in particular, this integral, if you kind of work it out and see what that integrand, that outer integrand ends up being, it's not nice. It's got a polynomial times square root of 1 minus x squared. So it's going to be a combination of trig substitutions and clever integration by parts and fractions and other annoying things that nobody really wants to deal with. So I'm going to say this is not the way we want to do that problem. So let's try the change of variables. Again, we're going to use polar coordinates as our change of variables function. I claim that the pullback domain will be this. Now, let me walk you through that argument that this is the pullback domain. We're going to take it one edge at a time. Let's start with this edge right here. In the r theta plane, notice that this is in the plane theta equals 0, okay, which is that right there. And in particular, this is where r goes from 0 to 1. So specifically, it is this edge right there. Continuing along, let's look at this, color change. Here we go. This edge right there. Well, that is on the line r equals 1, which is the unit circle. But specifically, this is the line r equals 1 between theta equals 0 and theta equals pi over 2. So specifically, it is this edge right there. Everybody with me so far? Yeah, okay, and then moving along, this edge there is part of the line theta equals pi over 2, which is that blue line. But specifically between r equals 0 and r equals 1. And so it's specifically this edge, like that. Okay, so now the last, this is a little bit of a weird one, this edge right here, notice that's on the line r equals 0. However many points you have on r equals 0 in the xy plane, that's just the origin. There is only one point where r is equal to 0. So, okay, so the big idea then is you look at which edges go to which edges, and you notice that then all of this area inside of those lines gets mapped into all of this area inside of those lines. And as desired, we have ourselves a pullback domain. Okay, so with that noted, I'll further observe this pullback domain is a rectangle, which we like. R and theta have these bounds. Matter of sort of looking at the geometry there. And we're kind of in business. Now, a couple little details. Make sure you don't forget. It's really easy to forget the stretching factor. Remember, whenever you do a change of variables, you have to insert that stretching factor in there. Arguably, that is the sophisticated point. That's the big multivariable calculus idea, is that the stretching factor is something you have to stick in as you kind of plug in. Everything else is mostly just plugging in its various forms. So the stretching factor, a huge deal. Please make sure you don't forget it. it's unavoidably worth points. You can think of that as a good thing or a bad thing. I prefer to see it as glass half empty, that, hey, free points. All I have to do is remember the stretching factor. But the flip side of that is, don't forget the stretching factor because it's worth a lot of points. Okay, so all you got to do is make sure to remember it. Let's see here. And then, of course, you've got to convert from rectangular to polar. So x squared plus y squared, conveniently, easy to write in polar coordinates. It's just r squared. And we're in business and single variable calculus and answer. The only other little detail that I do want to point out, I've seen a lot of students make the following mistake. Notice that our integrand for our new pullback integral is r cubed, right? And thus antiderivative 1/4 r to the 4th. But here's the mistake that a lot of students make. A lot of students, this is just my experience over the many years, feel like that the r kind of has to stay with these differentials, and that the integrand therefore should just be r squared, and then they take an antiderivative of just r squared. And that's just completely missing the point of what the purpose of the stretching factor is. The stretching factor needs to be there for the purpose of being part of your new integrand, just like with substitutions back in single variable calculus. So make sure to actually not only include the stretching factor, but make sure to combine it with your previous integrand to get your new integrand. Okay. All right. So there's our first example. Now, I'm going to take a different point of view on this example now. I think this is a really useful point of view. Different ways to say this. You recall that when we're up here in the r theta plane, we do various kinds of slices. So, for example, I do theta slices that look like this, right? And then for each theta slice, I do r slices. The r slices are technically like this, but I'm looking only at the r slices of the theta slice, so I'm kind of just moving along that theta slice. Okay, well, those slices, theta slices like this, for example, I can just see exactly what those look like in the xy plane. After all, each one of those theta slices, it just represents a constant value of theta. And I can tell you exactly what those constant values of theta look like in the xy plane. They just look like little sort of radial sort of rays coming out of the origin, like that. So, for whatever that's worth. And then likewise, r slices, like this, constant values of r. Well, I can see those in the xy plane as well. Constant values of r are just kind of pieces of circles like that. So, the point of view we're going to take then is that instead of slicing up the pullback domain explicitly, I'm going to kind of implicitly slice up the pullback domain by just looking at what those slices look like over here on this picture that I already have. And I can see it just as well, and I already have that picture on the right, so might as well use it. Okay. All right, now there's a different way to say the same thing, just a different point of view. Instead of, you might say, pulling back the domain and then slicing up the pullback domain, I'm going to push forward the slices of the domain. Instead of pulling back the domain, I push forward the slices. All right. Like I say, just a different point of view on the same thing. Let me show you what this looks like in practice. Here's that exact same example that we just got through looking at. Again, we started with this quarter disc. And that quarter disc, we did the pullback. We found that the pullback was this rectangle. We sliced up the rectangle, blah, blah, blah. Now, you'll notice I'm going to scratch that off here. I deliberately leave it visible so that, if you want to look on the scratched out portion that we're ignoring to make a, comparison or reference, it's there. Feel free. But let me show you how you can go through and get these same bounds, get the same polar integral, without looking away from this picture at all. And that is step one. Of course, we got to do the algebraic bit. We got to rewrite dx dy as rt theta. Again, don't forget that stretching factor, huge deal, lots of points. Make sure to get that in there. The integrand turns into polar coordinates as well. And now let's just play bound games. What's the range of values of theta? I don't need to look at that picture. Theta starts clearly at theta equals 0. And then my theta slices kind of move along like that until eventually I get to evidently my last slice, which is there. That's my last theta slice before I'm missing completely, and that's clearly where theta is pi over 2. I can see it right there in the picture. My existing picture, I don't need this pullback picture at all. Again, scratched out. Then looking at an arbitrary theta slice. Now moving on, let's ask what's the range of values of r? Well, on that theta slice, there's the lowest value of r. There it is. There's that lowest value of r. It's clearly at the origin, where r is, of course, clearly 0. So our lower bound is 0. And for the upper bound for r, for the upper bound for r, that's this point, which is on this curve, which is this equation. Don't forget it's a unit disk. And solving for r, there's my upper bound for r. Everything happened on my existing picture in the xy plane. I did not have to draw the pullback at all. Now, to be clear, it is still a pullback. It is still a change of variables. Absolutely. This is just a way of avoiding the extra inconvenience and challenge of drawing the pullback. Right? So it's still change of variables. It's still a pullback. This is just a streamlining of the process. Pausing for questions. Anybody have any questions about this? We got a bunch more examples coming. Okay. All right, so we'll proceed to the next examples. Here we go. We're going to compute, let's see here, this integral. My domain is the unit disk. That's this entire unit disk there. Okay. You kind of have some options here in terms of how you slice this up. You could say there are lots of different options for pullback domains. I'm going to show you what I think is kind of the easiest way to think about this. I would like to think of this as we start there where theta is equal to 0. Let's see here. So our theta lower bound starts at 0. And then theta, well, it kind of, if you will, goes all the way around. Right? My theta slices, in other words, kind of, they keep going all the way around. And then I end, get off of there. I end at, there, which kind of looks like just where I started. And there's a temptation to say, I previously called that 0. Shouldn't I again call that 0? But you can't. You do have to remember, theta increased and by a full turn to get to that point. Now again, it looks the same in the xy plane, but again, keep in mind there actually is a pullback domain where theta increased by 2 pi. So this ending value I have to interpret as 2 pi, thus giving me my upper bound of 2 pi. All right. You do have options on this. If you want to think of this as starting at negative pi and going around to positive pi, also cool. There are some situations where that's even advantageous. Most of the time, I like to arrange for to get zeros when I can. I like zeros, so 0 to 2 pi is kind of I think the more standard, typical thing to choose. But again, you have options. Okay, now we fix a value of theta, and we move on to finding the range of values of r. Where does r start? Well, r starts there at the origin. where r is clearly 0. And r ends at the boundary of the, don't forget, unit disk, where, of course, r is equal to 1. Everybody with me? Everybody's happy? All right. Okay, so, again, don't forget. So easy to forget. Very important not to forget. Be sure to remember the stretching factor. Right, that R right there, that one factor of R is the big idea, the big multivariable calculus concept. So you've got to make sure to get that in there. Again, glasses half full, easy points. Right? Don't forget to take the easy points. Okay. All right. And then, of course, the ensuing calculus, very straightforward and nice, easy answer. Okay, so here's some tips and tricks, and we're going to, again, more examples to come, but nice tips and tricks. Turns out, vast majority of cases, so almost always that I think it's fair to just say always asterisk. I mean, technically there are some weird examples where to the contrary, but practically always you're going to want to do it in this order. dr d theta. dr on the inside, d theta on the outside. Practically always. Okay. About that stretching factor, I'm a big believer in this move right here. Always write r dr d theta all together. Don't ever just write dr d theta by itself. Dr d theta by itself is not really a thing. Right? If you think about it, if your integral came to you as a region in the xy plane, you're doing an integral on the xy plane, dx dy, then dx dy is the thing. And r dr d theta is what dx dy is. Dr d theta by itself, not. So just don't ever write it by itself. And if you make a habit of this, that you always write r dr d theta as a single unit, all at the same time, it's a nice sort of security move, sort of protection against inadvertently, accidentally forgetting, which you would be surprised how easy that is to do. And again, this is years of experience teaching this class, this and equivalent class to Math 212. It's just amazing how many students get distracted very understandably by the picture and the slicing and the bounds and all of that, and then they just forget about the stretching factor. So easy to make that mistake. Don't let that be you. So again, if you just write these all together, you're good. Yes? Yes, that's right. Well, now I say always if you are doing your integral using the polar coordinates change of coordinates function as your change of variables function. So it becomes kind of a trivial statement because this is in fact only one function and it has only one stretching factor. So yeah, that's right. Yeah. Right. And by the way, you don't have to show this calculation. This is and you should do it once. Everybody should do it once. Right? But on an exam, unless it, unlikely, if I conceivably, I might ask a question that says, derive the polar coordinate stretching factor or something like that. In which case, you'd have to show your work. But other than that, you can just cite the stretching factor. Okay. All right. And then don't forget we understand, stylus. We understand our bounds as coming from geometric observations about which points do those bounds happen at, and which curves are they on, and which equations do they have, which I can then solve for the bounds, just like with every other kind of integrals we've ever done. Okay, more examples. Suppose you want to. Question.
So it means how do you determine the bounds without looking at the graph?
I don't understand. I'm sorry. What?
When you do the transformation from xy to ub, how do you
like this right here, like this sort of a.
Oh yeah.
Okay.
If you have a complex equation.
And you want to do it without looking at the picture?
Yeah.
That's not a thing.
Oh,
Yeah, you really need a picture. I mean, there are some rare circumstances where like I had one again as an undergraduate one time where it was a 6-dimensional integral, and I couldn't draw the picture, and so I had to make some purely algebraic arguments to derive the bound, and it was rough. That was hard. And it's not something that's a good idea in a situation like this. In this class, everything's going to be dimensions 3 and down, and you really should always have a picture. Yeah. I just, practically speaking, it's just the only way to go. Yeah. Does that make sense?
Yeah. So then if we had like a graph in X and Y, and then like it's not a simple graph, how would you find the balance for that?
Everyone's different. Right? I mean, so it always depends on the shape. You've got to just look and see, what do my theta slices look like? Where's the first one? Where's the last one? Every picture is different. So the best I can do there is just show you a bunch of examples, which is what we're about to do. Yeah. I wish there were a single, algorithm, but it's always very, very case dependent. Yeah. Okay. All right. So, here we go. So let's look at this domain here. We are talking about this, the domain here is this annulus, we call it. That's this, kind of ring-like thing here. I enjoy viewing this as being a moat around a castle. I don't know why, I just like it. So, that being our domain, maybe we're computing the amount of, the volume of water in the moat, let's say, right? How would I compute this integral right here? Okay, well, here's the first shot you might take at it. Very strong temptation and a reasonably good idea, at least initially, is to say, let's look at this integral over this disk and then subtract the integral over this disk. Right? The whole yellow thing minus the orange thing should leave you with the moat that we're interested in. Very, very tempting. And were it not for a very particular problem here, that could have worked. But the very particular problem is to look at the integrand and realize that this integrand is not defined at the origin. Right? There is a nasty, explosive singularity there. Right? It's not just not defined, it's approaching infinity. So serious discontinuity there, which means that neither of these integrals is even defined in the first place. So this doesn't work. This is a non-starter. Does that make sense to everybody? Can't do it. Okay. By the way, you might be tempted to make some sort of an argument with improper integrals. Y'all remember that was a thing from Calc 2. Turns out defining improper integrals in a multivariable context is fraud. There's issues there. So that's not something that's Math 219 appropriate. Okay, second approach. We could say, all right, well, I'll chop it up into 4 pieces like this, and I'll do it in rectangular coordinates, the old-fashioned way, and you could do that. That would work in some technical sense, but that's 4 separate integrals. Nobody wants that. Worse, it's 4 separate integrals with square roots and the bounds all over the place. This is a nightmare. Don't want to do it that way. Okay, so here's the move. Use polar coordinates. Our theta slices, no problem. Our theta slices, you'll notice, go all the way around. So theta theta slices just go from 0 to 2 pi. No problem. Then for a given value of theta, let's think about the values of r. Well, r starts at that point, which is on this curve, which has this equation, which then gives us our lower bound of 1. And then r ends at that point, which is on this curve, which has this equation, which gives us our upper bound of 2. But nothing to it. Is everybody happy with that? Now, you could be still concerned, yeah, but what about this fraction. And don't we still have an explosion problem? Well, there's two reasons we don't have an explosion problem. For one thing, dx dy, don't forget your stretching factor, right? Dx dy turns into RD theta, which makes my integrand actually not a fraction at all in this case. So really not a problem. And second of all, notice here, R is never 0. The way I'm doing this. There's no R equals 0 problem. So even if there had been a fraction left, it still wouldn't be a problem. No problem at all. And this is a super easy integral. Integrand being a constant. And you can crank that out yourself and you get 2 pi. Everybody okay? All right. Okay, next one. A little harder. Weird shape here. We are going to start with, you'll notice here a disk. That's this disk like this. But specifically we are then going to exclude, that's what this backslash means. This says eliminate from the blue every point in that disk. Which is this right here. And so if you take your blue set and you then remove from it every point that is in the orange set, then what you're left with is this gray shaded region that I have here. That's what this is. This region right here. How y'all doing with that notation? Is everybody comfortable with the notation? Okay, how are we going to do an integral on this? Again, if you do this in rectangular coordinates, it's a nightmare. It's whichever way you slice, you're going to have 3 pieces. And you can choose which kind of 3 hard pieces with square roots you get, but it's going to be 3 hard pieces with square roots, and nobody wants that. Okay, so we're going to do this in polar coordinates. RD theta. Again, notice I've already not forgotten my R. Right? So I'm a big fan. Please do this. Please, unless you have a better way to remember, that's also fine. But this is the only way that I can stop myself from accidentally forgetting 10% of the time to put my stretching factor in there. Okay, so let's see here. Oh, and then of course X is R cosine theta. That's easy as well. Okay, so what can I say about my theta slices? Theta slices, of course, emanate out of the origin like this. And specifically then, an actual theta slice looks something like this here. Where's the first one? Where's the last one? Well, the first one is at this point right there. We'll worry about the last one in a moment. What can I say about that point right there? I'm going to give you 2 options for how you might identify what the value of theta is there. One option, you can take that curve, find its equation, that curve, find its equation, realize that you're looking for a point that satisfies both, and then solve for theta, because that's what you're trying to find. Solve for theta in that pair of equations. That'll work fine. It's not even all that bad, but it is a little bit less convenient than this other move I'm going to show you now. This is slick, purely geometry. Notice that that distance and that distance are both radii of that circle, which has radius 1. And then notice that this distance is a radius of this circle, which also has radius 1, and that means that all 3 edges of this triangle have length 1. That makes this what do they call it? An equilateral triangle. Y'all have studied equilateral triangles. You know that angle is pi over 3. And then with that in mind, and remembering that what we're looking for is a value of theta measured off of the positive part of the x-axis, we see that this value of theta is negative pi over 3. Yes?
We set the polar equations to be equal?
Yep. Well, no, you don't set equations equal. But what you have is a pair of equations, and then you solve for the thing that you want, namely theta. But is that what you meant?
Yeah.
Yeah, okay, yeah, cool, totally. So yeah, you could do that. Again, sometimes you get lucky and something, fortunate geometry presents itself. And in cases like this, I'd, advise you to take advantage of the good luck when it comes up. Okay. Very similar argument will allow you to find this upper bound. This is an equilateral triangle also. Very similar reasoning. And so upper bound positive pi over 3. All right. Okay, so that said, we are now going to focus on a single theta slice. And now we look for the range of values of R. And our R starts at this point, which is on this curve, which has this equation. Solve for R. We get 1. Upper bound for R, again, we're just looking for a value of R. Our last value of R is this one, which is on this curve, which has that equation. Now let me pause. Where did I get this equation from? Well, okay, that's the boundary of this set. The boundary has this equation. You just make the inequality an equation. And then you convert into polar coordinates a la chapter 1. So I did just skip over a bunch of algebra there. Make sure you're good with that algebra. Again, it's all chapter 1 stuff. You've done it before, right? But make sure you're proficient. So namely, reliable and quick. With doing this conversion, the equation ends up being this, and again, that's going to give you this formula for R. Okay. Everybody all right with that? So we're in business. We've got our lower bound. We've got our upper bound. We've got the whole iterated integral now. And this integral, not that bad. It's got some trig in it. Trig can be a little bothersome, right? But the alternative was 3 separate integrals with square roots in them, right? And honestly, any time you give me a choice between integrals with square roots in it and integrals with trig in it, I'm going to take the trig integrals every time, because trig integrals give me the tools called trig identities to work with. They're very, very handy tools for doing trig integrals. With square roots, all you've got is kind of the algebra of square roots, which it's just not as good. So this is not only 1/3 as many integrals, it's also better individually as a single integral. Okay. Moving along. This one's of historical interest. This was a famous calculation that happened a couple hundred years ago. It relates to statistics. If you've ever had a stat class, or if you've ever had a Calc 2 class that included some stat, you may recall that probabilities get computed as integrals of these things called probability density functions, sometimes called distributions. So this one, in particular, is called the normal distribution. It is extremely important. It is not just important for arbitrary reasons. It's for fundamental mathematical reasons. This is intrinsically natural. And exactly how and why is a longer conversation that we can't go into. But the naturality of this distribution isn't even just mathematical. It shows up in biology, weirdly. It shows up in real-world scenarios all over the place. Again, ultimately because of mathematical reasons. So anyway, this integral, being as it is an integral, that's how you compute probabilities of arguably the most natural and fundamental distribution, is a big deal. Very important to be able to compute this integral. Bad news. There is no antiderivative for this function. We talked about that before. It just doesn't have one without using Taylor series. And so we can't use the fundamental theorem. We have an integral to compute, and we can't use the fundamental theorem. So we're in trouble. This is a big problem. Here's the move. I never would have thought of this in a million years. I'm convinced. This is extremely clever. I think a lot of mathematicians never would have thought of this in a million years. It's extremely clever. So here's, again, really clever idea. Here we go. This thing we want to compute, we're going to give it a name. I'm going to call it J. And then I'm going to write down j squared. After all, that's j. And frankly, this is j too. It looks different. It's got a y instead of an x. But that's just a dummy variable. Whatever. Right? There's nothing magical about particular letters of the alphabet. They're just placeholders. So what we're going to do is now we're going to look at this product and we're going to do some weird moves that are going to be legal but seemingly hard to motivate. So follow along, even though this is going to seem like we're going in the wrong direction. Play along. I promise it's all going to work out. Here's the first idea. Let's look at this this dy integral. Don't forget that this thing over here is in fact just a number. It's j. It's some value. We don't know what it is yet, but it is just one value. It's a constant, and constants can go inside of integrals. Right, that's just the linearity of integrals. Factor it into the integral. No problem. Okay, next move. Now we have an integral inside of an integral. Let's look at this inside integral now. This dx integral. This dx integral. Don't forget that the variable further to the outside, also constant as far as the inside integral is concerned. That means e to the negative y squared is a constant and can go inside of the integral. It is a constant. So that's also legal. Everybody with me so far? Yep. I'm sorry, speak up. Yeah, it's a constant for the purposes of the blue dx integral because it's further to the outside, right? Y is the variable to the outside, so y is a constant as far as that dx integral is concerned. Yeah. Now, one thing I want to confess, now we're good down to this point, but it looks like we're going the wrong direction. I started off with a problem that I've recognized that I don't know how to do, and I've now successfully turned that question into what at a glance looks like a harder problem. So it seems like I'm just making it worse. Right? Here's where the beauty kicks in. This is a double integral. Right? I'll do it like this. Dx dy is dA. These values of x and y just take you over all of R2. X and y both going over all possible values. So I can think of this as just a double integral. That opens some doors. Now we don't just have single variable calculus techniques to work with. Now I have our entire toolbox of multivariable calculus techniques to use. That includes some tools that we did not have in single variable calculus. In particular, we did not have polar coordinate pullbacks in single variable calculus. It's not a thing. And using that here, dA, of course, is rd theta. X squared plus y squared, of course, is r squared. And all possible values of x and y mean that r and theta range over, well, all possible values. I just got to be able to sweep out the entire xy plane. So theta goes all the way around, and r goes from the origin all the way out in all different directions. And now let's look at what we've turned this into. This double integral, now written in polar coordinates. Looking at the inside integral, that exponential now has an extra factor of r sitting next to it, and it's now an easy substitution. Just let u equal negative r squared, and it's all, falls apart. And it's just boom, instant. It's there's 3 or 4 steps, right? But totally doable, and y'all can work that out. It's a nice calculation, and the answer is pi. Don't forget what we were computing there was actually j squared. That was pi. That makes j square root of pi. So very, very clever. This is the only method that I'm aware of for computing this very important integral. So very clever move. Famous calculation. Yes?
So you know how we move the integral, the negative x squared and row into the e to the negative y squared. Because
Yeah.
that is enough.
That's right. This is just a number. That's right. So I toss it into here like so. That's right.
So any calculation of this one, we would have to think, can we always assume that the intervals are going to converge, that they are going to give us the actual?
Oh, that's a great question. Yeah, I did kind of sweep that under the rug. Yeah, that's a really great point. I think in order to really be honest about this, I should have made a convergence argument. It's not hard to make such a convergence argument. It's easy to put an upper bound, like e to the negative x squared is very quickly, easily seen to be less than 1 over x squared for sufficiently large values. And so, that should be thrown in there. But the fun part of the calculation is what we've got here. Great point. Thank you for that. Yeah. I'm going to call that kind of a formality that we don't need to worry about. Okay, so again, polar coordinates for the win. Really nice. All right. Okay, so we're going to move on now and talk about cylindrical coordinates. Cylindrical coordinates is just like polar coordinates. And again, you can do a pullback and you can draw your pullback domain. Sure, fine, feel free, go ahead, change the variables and all that. But notice again, you can see your r, theta, and z slices in XYZ world. So you don't really need to draw the pullbacks. This theta slice right here, it just represents a constant value of theta, which is just a half plane hinged on the z-axis. So, again, just like with polar coordinates, I don't need to pull back my domain. I can just look and see what these theta slices look like in XYZ space. Namely, I can push forward the theta slices. And etc. So let's see some examples of this. Oh, real quick, just some tips and tricks. You got 6 different options for how to order your differentials. It turns out that the only ones you really need to entertain are the ones that keep dr and d theta together and in that order. Don't even think about anything else. Dr, d theta have to be together and in that order. And then, of course, dz can either be outside or inside. Those are the options. And that's it. So there's really only these 2 orderings. You shouldn't even consider any of the other 4. Again, just like with polar coordinates, don't forget your stretching factor. Very easy to forget. Very big deal. It's the big multivariable calculus concept as a tool to prevent yourself from accidentally forgetting that we're all susceptible to, right? Myself included. Just think of this as a single thing. After all, this is dv. This is dx, dy, dz. This is the thing. Dr, d theta, dz by itself is not a thing. It's got nothing to do, by itself, nothing to do with anything. So it doesn't make any sense to write it down by itself. Always write this as a whole. And again, if you can make yourself follow that rule, and I do my best myself, and I forget sometimes, and oh my gosh. But if you can follow this rule, then you will be safe. Well, you'll be more safe from forgetting that stretching factor. Okay. All right. Example. Upper half ball, radius A. There's my domain. Let's slice this up in cylindrical coordinates. Notice there's my stretching factor. I've already not forgotten it. Right? Just writing this down right here is worth points. So I'm on the board already. Right? So now we slice, and we start with theta slices. Theta. Oh gosh. There we go. Theta slices, again, half planes hinged on the z-axis. Slicing up a half ball gives me slices that look like that. Easy case to make that they go all the way around. So 0 to 2 pi. Okay. Now, we focus on a theta slice. What do R slices look like? Well, R slices are cylinders. Oh gosh, if I can draw cylinders centered on the z-axis. How does a cylinder intersect with that theta slice? Well, it's this little line segment right there. So that's an R slice of a theta slice. Is everybody with me geometrically? Okay, first and last. First slice is there. We're pretty clearly, we're on the z-axis, and so R is 0. Last slice is going to be there, which is on the edge of the ball, which has radius A, which means that R there is A. So 0 to A. Okay, then we fix a value of R. Now we move on to Z slices. What's the range of values of Z? Well, Z starts there. What can I say about Z at that purple point? Well, we're in the XY plane there. By the way, the picture, it tells all, right? So notice I'm working off of nice, big, reasonably drawn pictures. Make sure to give yourself good pictures. It's unavoidably important. And being as this point is clearly in the XY plane, 0, right, for our lower bound for Z. Our upper bound for Z is going to come from looking at this point. And what can I say about that point? That point, well, it's on our sphere. Flashback to chapter 1, the cylindrical equation for a sphere is this. Now wait a second, we just did some geometry and some algebra, and I forget as I'm doing these, wait a minute, what am I looking for here? I have to come down and remind myself, I'm looking for a value of Z. So in this equation here, I need to solve for Z, which gives me that, which gives me my upper bound. What do you think? Everybody see what happened there? Now, a lot of this, by the way, you'll notice a lot of this, it's morally, it's kind of the same process as with regular triple integrals. It's just different shaped slices, and don't forget your stretching factor. So, okay. All right. Real quick, last thing I'm going to do is talk about slicing it the other way. Arbitrarily, you'll notice, of course, I did dz, dr, d theta. Now we're going to do dr, d theta, dz. Notice I've already not forgotten my stretching factor. Again, I'm on the board. Points on the board already, just from putting that r in there. So again, I urge that you do the same thing. Always write down r, dr, d theta, dz as a single thing for that purpose. And with that in mind, let's start doing our slicing. What's the range of values of Z? Well, Z slices look like that, giving us cross sections that are discs like this. The first one of which is down here, where Z, let's not forget we're looking at Z, is clearly 0. Last slice, North Pole. Whereas Z, don't forget, again, looking at Z, at the North Pole, of course, this is a sphere of radius A. Z is equal to A. Then, as usual, we're now going to fix a value of Z. Looking at that Z slice, now let's talk theta. What can I say about theta? Well, theta is going to go all the way around. So, 0 to 2 pi. No. And then lastly, looking at our theta slice, an arbitrary theta slice there. Let's see, what is remaining? We're looking at R now. R starts there at the origin. What is R? I keep saying origin. The z-axis, right? What is the value of R on the z-axis? Well, the value of R on the z-axis is 0. So my starting value of R is 0. And then my ending value of R in R, that point. What can I say about that point? Again, thank you, picture. The picture tells all. From the picture, what I can see is that point is on the sphere, which again has this same equation as in the previous example. Now, sticky little point, easy mistake to make. Notice here, I am looking for an R bound. Previously, when we wrote down that equation, we'd been looking for a Z bound because we had our differentials in the other order. And so, we have our differentials in this order now. So we have to appropriately, since we're solving for R, since we're looking for R bounds, we need to solve for R, which gives us that formula for our upper bound. Everybody all right? Any questions? All right. Okay, let's see. We have, we're long out of time. Okay, so sorry, went a minute over. Drawing the line right there, we will pick up with spherical coordinates on Friday. See y'all later. Have a good one. Yes?
For the homework, is it going to be the part one?